Welcome back to Physics 141 Online. We're doing lots of problems where we use the principle of conservation of energy, and I'd like to do another one like this that involves two masses hanging over a pulley. We did some problems like this previously using Newton's second law, but we're going to ask a different kind of question that we can answer most easily using the conservation of energy. So take a look at the problem. These two masses, m and 3m, hang over opposite sides of a pulley, and we're going to neglect the mass and any friction involved in the pulley. So if these masses are released from rest at the position shown, we want to find the speed that they have when mass 3m hits the surface after falling a distance d. So our answer should only be in terms of m and d and maybe the Earth's gravitational acceleration g and some numerical values, some numerical constants. So let's see what we need to do. And first of all, look at what we're actually trying to find. We're trying to find the speed. And you'll remember that in Newton's laws, speed or velocity doesn't enter into at all. We could solve this problem and find the acceleration of the masses while they're moving, and then if we know the acceleration and we know the initial velocity, we could find the velocity after they've traveled a distance d. But if we really want to just find the speed, using conservation of energy will allow us to get that quantity directly without having to first calculate the acceleration. And one nice thing about conservation of energy is that if all the forces that are acting in the problem have potential energy functions that we can write down, we don't have to use Newton's second law. We don't have to even worry about putting forces into our treatment of the problem. So, in this problem, let me just write down what the overall equation is going to be that we're going to use. We're going to use this master equation for the principle of conservation of energy that says the sum of the initial kinetic and potential energies plus any work done by a non-conservative force, like friction, is equal to the sum of the kinetic and potential energies for the system at the end, initial and final. And so the initial configuration, that's easy, that's what we have in the picture. The final configuration, and I'll indicate this, the positions of these masses using some dotted lines. Here, mass 3m will have hit the surface, so that's going to be the final, and mass m will have gone up a corresponding distance, so it will be a little bit higher than it started out. And those two will represent the final configuration. And we can see, just by thinking about this problem, we're trying to find the speed of the masses, and as long as that string doesn't stretch, that speed is going to be the same for both. So in other words, if mass 3m falls a distance d, it does so in the same time that the other mass m goes up a distance d. And so their speeds have to be the same, although the directions, of course, would be different. But the kinetic energy equation only involves speed. So those two v's, we can use the same v for each mass. And we know, of course, that v initial is equal to 0 because the system has, or the problem tells us that the masses are released from rest, so that v initial is 0. We'll plug that in just a second. All right, now we want to therefore write down expressions for each one of these terms. And the initial, I'll write them down here and then we'll plug them in. The initial kinetic energy, we can just immediately say that's equal to 0 because the two objects are at rest. The work done by any non-conservative forces, of course, that would be 0 unless there's some kind of frictional force acting. And so assuming that there's no friction means there's no work done by a non-conservative force. The only forces acting are the gravitational force, of course, and the tensions we don't have to worry about because the tensions are acting on the two masses in equal and opposite directions. And so thinking of the two masses as a system, if we take them together, one of them experiences an upward force due to the tension, and the other one experiences the same upward force, but the work that's done by those two tension forces would be equal and opposite. And so they would add up. Even though the tension is a non-conservative force here, they would add up to be zero as well. So what about the potential energy initial? U initial. For each object now we're going to have to write down mg times the height. So we have to do two things. We have to decide where we're going to measure the height from, and that's pretty easy. Let's just be simple and measure it from the ground, from the surface down here. And then we want to be able to write down the potential energy for mass m. For 3m it's easy because we have a symbol that tells us its height, but for m we're not given any kind of height, and so that means we've got to put it into the problem ourselves. So let's just call the initial height of m above the surface a. I'm putting it in, and I don't expect that it should end up in the answer, but I've got to put it in here in order to write down the initial potential energy function. So for mass m, it would be mg times a, and then we have to add that to the potential energy of mass 3m, so 3m times g times d. So remember, this equation is in terms of the kinetic and potential energies of the entire system, and we've defined the system as the two masses together. So that's U initial. Now what about U final? Let's go ahead and write down U final, and then we'll write down K final. U final is going to be now mass m has gone up the same distance that mass 3m has fallen, a distance d. And so mass m is now going to be at a height of a plus d, and mass 3m has fallen down to the ground, to the surface, so its height is 0. And so there won't be a potential energy term for mass 3m in the final configuration. The only thing then left to do is write down the final kinetic energy, and here both masses are moving. So we're going to have 1/2 times m times v squared, its speed squared, and then we're going to have 1/2 times 3m, I'll put parentheses around that, times v squared, because it's also moving with that same speed v. So 1/2 mv squared plus 1/2 3m times v squared, and that's the total kinetic energy in the final configuration. So we've done the hard work. All that's left now is substituting into this equation and then handling the algebra. So we know the kinetic energy term initial is 0, work non-conservative is 0. So what do we have? Well, let's write this down. I'll bring it down here because I need a little bit more room than I've left myself. So the initial U is mga plus 3m gd. All right, and that's all that's on the left-hand side. The right-hand side, kinetic energy final. So let's see, what do we have here? 1/2 m, and then this term, the second term, is 3/2 m. So we've got 1/2 mv squared plus 3/2 mv squared, and we can see, just a minute, we'll combine those and write that as 2 mv squared. But then the last term is the final potential energy, and that's just mg times a plus d. So I'm going to multiply that out. mga plus mgd. So everything's been substituted in, and notice what you'll see. There's a term on each side that says mga. So if we subtract mga from both sides, those two terms drop out, and that's the only place where that distance a entered into the equation at all. I said in the beginning I'm going to have to put that in so that I can write down the potential energy, but it turns out it drops out of the problem. So that distance a does not affect the answer. So what do I have? I've got 3 mgd on the left and then mgd on the right. So if I subtract that from both sides, I'll get a result on the left-hand side of 2 mgd, and then on the right-hand side, 1/2 plus 3/2 is 2, so this becomes 2 mv squared, and you see that if I divide both sides by 2m, that drops out, so I end up in the end v squared is g times d, or v equals square root of g times d. And we can check the answer For units, let's just check to make sure that we've done our algebra correctly. We haven't made any horrible mistakes. So according to this equation, the units for velocity should be the units for g, which are meters per second squared. The units for d, that's a distance, so that's times meters. So under the square root, we got meters squared per second squared, and that gives us meters per second. So the units check out, and the answer turns out to be surprisingly simple for this problem. So I hope this is helpful as you tackle these kinds of problems on your homework assignment and potentially on quizzes and exams. Remember, all we did was realize this was a problem where we want to use the law of conservation of energy because we were asked to find a speed. And kinetic energy is related to speed. So this was not a Newton's second law problem, although you could solve it that way. It would just involve more work. And once we realize that, we then write down each of the terms in as much detail as we can. We write them all down here. Then we substitute into the original conservation of energy equation, do our algebra, and solve for the final speed. I hope this is helpful, and I'll see you in class.